We present a method to reconstruct physically plausible 4D scenes from monocular videos. This is work with Shuo Yang, Zhang Zhang, Zachary Manchester, and Deva Ramanan. In recent years, there has been exciting progress in deformable object reconstruction from images and videos. Our goal is to build models of both the object and its surrounding scene in 4D, which satisfy physics constraints and can be replayed in a simulator. In monocular reconstruction, there is a fundamental depth ambiguity due to camera projection from 3D to 2D. This Eiffel Tower could be toy-sized held by a hand, or the real one that's far away. If the scene is rigid, multiple views can reduce the ambiguity to global scale factor. However, for non-rigid scenes, having multiple frames does not solve the problem. Here we increase the scale of the cat while freezing the background. This leads to different 4D reconstructions, but identical 2D projections. Depth ambiguity also leads to ambiguities in 3D body pose. Although the reconstruction of the dog can explain the reference image fairly well, it is physically unstable because the center of mass projects outside its support polygon. In simple terms, a 3D print of this shape will fall over. Our goal is to fix such errors by incorporating a physical simulator into the reconstruction process. Prior approaches first estimate kinematics, and then use the physics-informed optimization to post-process the reconstructions. When naively doing this, we find the physical reconstruction diverges from the visual evidence due to physically implausible kinematics. On the left, the reconstructed cat is not making contact with the ground. As a result, the physical model fails to track the kinematic reconstruction. Ideally, we want to directly optimize the physical model to match the visual evidence. This involves simulating a trajectory and then rendering them in a differentiable manner. However, this optimization is challenging because differentiable rendering and differentiable physics have different optimization landscape, and they favor different sampling strategies. For example, differentiable rendering converges better if we sample pixels uniformly. However, for differentiable physics, sampling trajectories over a long time horizon better enforces dynamics and contact constraints. To deal with this problem, we solve it with coordinate descent optimization, which alternates between solving kinematic reconstructions and fitting a physical model. The kinematic reconstructions include the rest appearance of objects and scenes, as well as kinematic parameters. Given input videos and their extracted features, we use differentiable rendering to minimize the difference between the synthesized images and the observed images. The physical model includes the body mass distribution and control torques. We use differentiable physics to minimize the difference between simulated motion and the kinematic targets. To recap, we are solving kinematic reconstruction and the physical parameters by alternating between a differentiable rendering step and a differentiable physics step. In each cycle, we first optimize the kinematic reconstruction, where we only need to compute the differentiable rendering term, and the physics term becomes a regularizer. We then optimize the physical parameters by computing the differentiable physics term using the frozen kinematic reconstruction as the target. After multiple cycles of coordinate descent, the parameters converges to a better solution that is faithful to the input video and can be tracked in a physical simulator. On the casual cat dataset, our method produces the most physically plausible results compared to baselines with minimal distance between the ground and the reconstructed cat. On the articulated mesh animation dataset, our method correctly estimates the human scale and foot contact locations. One application is to help real robots acquire natural motion scales from in-the-wild video footage without expensive marker-based mocap. To summarize, we introduce a method for reconstructing physically plausible 4D scenes from monocular videos. It uses differentiable physics to resolve visual ambiguities. This is enabled by coupling differentiable rendering and differentiable physics with coordinate descent optimization. Thank you.